Hi. In the previous segment, we introduced functions and some of the terminology related to them. In this one, we shall look at a few simple operations we can perform on functions, some of which will be familiar from the previous discussion of relations. The first operation on functions is the restriction. Given a function f from a to b and a subset x of its domain, you can think of the restriction of f to x as f with any of the tuples that map values not in x removed. You write it by adding x as an index to the name of the function, alternatively behind a vertical bar. You can see what happens to our example function when we restrict it to the set AB. Note that while restriction replaces the domain A with a subset x, it does not affect the codomain. The codomain of a restricted function is the same as that of the original. The next operation is that of computing an image, which is analogous to how one would do it with relations in general. The image of a set x under a function is simply the set of values in its codomain that the elements of x are mapped to by the function. Take a moment and consider these images. And these are the answers. There's one subtle difference between images of functions and general relations, which really is mostly about notation. In the case of relations, the image of a single value a in its source is a set of values in its target. The reason is, of course, that a relation may relate any value in the source to any number of values in the target, including none at all. So the image of a single value could very well be empty, contain a single image value, or any number of values in the target. The same is true for the image of a set of values in the source. It is a set of values in the target, and it could be any number of those, including none at all, in which case the image would be empty. With functions, the image of a set of values is still a set of values in the codomain. However, there is a difference when it comes to the image of a single value. If we talk about f as a function, we know that it must map every value in its domain to exactly one value in its codomain, by definition. Therefore, we will consider the image of a single value under a function to be an element of the codomain, not a set of elements. That is, not a subset of the codomain. This is, of course, so that we can use functions and their images in the way we're used to. Computing the image of a single value is simply good old-fashioned function application to that value. And the result of this is an element in the codomain. Another important operation on functions is composition. It can be defined as applying the functions one after the other. It is nothing but a special case of composition of relations. Whether you compose the functions f and g as functions, or you treat them as relations and use composition on relations, the result is identical. This is what this might look like in the bubble diagram representation. One interesting property is that function composition is associative. If you compose a string of more than two functions, the order in which you compose them, right to left or left to right, does not matter. That is why we can omit parentheses when writing compositions of more than two functions. The inverse of a function is also no different from that of a relation. It is simply obtained by inverting all the mappings the function makes. By the way, the term converse tends to be more common when discussing relations, while inverse is usually used in the context of functions for historical reasons. Mathematically, they are really the same thing. One thing to be aware of, however, is that the inverse of a function is not, in general, a function itself. Think about why that is and what property the original function would have to be so that its inverse would be a function. The inverse isn't a function because a function can map to any values in its domain any number of times, 0, 1, or more. When inverting, this then means that the inverse will map every value from any number of times. The inverse is a function, however, if the original function mapped every value of its codomain to exactly once, effectively creating a one-to-one mapping between domain and codomain. The next operation on functions, or perhaps it would be better to say with functions, pertains only to functions whose domain and codomain are the same set. We call such functions endofunctions. One way of thinking about an endofunction is as something that walks around within its domain. It maps a one value in it to the next, and then that one to another, and so forth. So one can think of applying that function to a value as a step or a move from one value in the domain to another. If we have a set of values in the domain, we call it closed with respect to f. If applying f to any of the values in that set will only ever give another value in the set. In other words, if a set is closed with respect to f, and if we start the walk with any value in that set, we cannot use f to get out of it, to reach a value not in that set. With this in mind, we can define the closure of some subset x of the domain of an endofunction f as the smallest set y that includes x and that is also closed with respect to f. Note that we express closeness here by saying that the image of y under f must be included in y. While this definition tells us what the closure of a set x under f is, it doesn't actually say anything about how we could compute it in practice. That is what this construction does. It works in a way similar to building the transitive closure of a relation, by building an infinite family of larger and larger sets and then throwing them all together in a union. We start with the set x itself and call it y0. Each subsequent yn plus 1 is built by taking the previous yn and then adding its image under f to it. This gives a sequence of y's, each including the former as well as all the values that can be reached from anywhere in the former set by one application of f, or one step, if you will. The union over all these y's is then the closure of x under f. This is a bubble diagram representation of our example function f. Since f is an endofunction, we can also drop the distinction between domain and codomain and represent it like this. With this, what are the values represented by these expressions? Take note of the kinds of brackets or parentheses used. And these are the answers. Let us look at a few more closures. In this case, the function is a function over the real numbers that just adds 1 to its argument. What is the closure of the set containing just 0 under this function? And what is the closure of the set of all negative real numbers under it? Repeatedly applying the increment function to the set containing just 0 results in all the natural numbers. Doing this with the negative real numbers yields all real numbers. For a few more closure examples, let us look at the square function over the real numbers. What are these closures? The closure of the interval 0 to 0.5 is that very same interval, since its image is already a subset of the interval and thus does not add any new elements. Put differently, the square function does not leave that interval for any values in it. The same is true for the interval from 0 to 1, whose image happens to be the exact same interval. In the case of the interval from 0 to 1.1, each subsequent y will become bigger than the original intervals, so the upper bound will grow forever, while the lower bound remains at 0. And thus the closure is just the non-negative real numbers, r plus. The last closure of the interval from 0.9 to 1.1, the upper bound grows as before, and now the lower bound decreases to become arbitrarily small, although it never reaches 0. Thus, in this case, the closure is the positive real numbers, or r plus without 0. Note, by the way, that in the last case, all the y's are closed intervals, but their union is open on both ends.